In this video, I'm going to show you one of the neatest problem-solving tricks ever. This is a technique that has saved me in many science and other kinds of classes where I needed a quantitative answer in college and high school where I didn't really know how to proceed. It's just a really good kind of an analytical wrench to approach lots of different kinds of problems and get the right answer and know you've gotten the right answer. This tool is called dimensional analysis, and it operates on two basic principles. One of them is multiplying by 1 does not change the size of something like a measurement. So 5 times 1 is still 5. 2 times 1 is 2. But that also means that if the number is really complicated, like 6.022 times 10 to the 23rd, if you multiply that by 1, it's still that same number, even though it's more complicated. And it doesn't even have to really be a number. It can be a variable that stands in for a number. So a times 1 is a. So that's one of the principles that dimensional analysis is built on. Multiplying by 1 does not change the size of something. The other principle is that the ratio of two things that are equivalent is 1. So 5 times 1 is 5, as we've seen before. But because 6 over 6 is also 1, 5 times 6 over 6 is 5. And because 4 plus 2 is 6, and 6 divided by 6 is 1, 5 times 6 divided by 4 plus 2 is also 5. And because 3 plus 3 is also 6, 5 times 3 plus 3 over 4 plus 2 is also equal to 5. Now here's where this becomes valuable. Quantities can also be equivalents of each other, measured quantities. So we were just looking at integers before. But here's an example of a quantity that's an equivalent. 1,000 milliliters is the same volume as a liter. So 1,000 milliliters divided by 1 liter, that's 1. That's like 4 plus 2 divided by 3 plus 3, because the two are equivalent to each other. Or 100 centimeters is the same length as a meter. So 100 centimeters divided by a meter is 1. And we could take the reciprocals of both of these too. 1 liter over 1,000 milliliters would still be 1, and 1 meter over 100 centimeters would be 1. Here's another example, 5,280 feet. Well, that's the same length as a mile. So 5,280 feet divided by a mile, we can think about that as 1. Some things are equivalents only in a certain context. For example, if the density of iron is 7.87 grams for every milliliter, then that means because 7.87 grams represents the same amount of iron as 1 milliliter, 7.87 grams divided by 1 milliliter is also 1. In the context of working with iron. So let's work out a few examples. Here's one. How long is a year in seconds? How you can do this is start out with the given amount. So in this case, 1 year. And then what we're going to do is we're going to creatively multiply by 1 as many times as we need to get our unit answer. So I'm going to put my target over here. I want this to end up in seconds. And then I have to just multiply by quantities that are equivalent to 1 until I can get the units to work out. Here's what I mean. I know that a year is 365 days. So I can put this ratio, 365 days over 1 year. I can multiply by that ratio, and it does not change the amount of time because 365 days is the equivalent of 1 year. But here's what it does do. Because I now have years on the top and the bottom, I can cross them out. And when I multiply these two together, the unit that pops out will be days. Well, that's not where I'm going, but it gets me in a direction where I'm going. So the next ratio I'm going to multiply will get rid of days. So I want to put days down here and get some other unit up here. Well, hours would be a possibility. I know that 1 day is the same as 24 hours, so I'm multiplying by 1 here, which does not change the amount of time. But because days now cancels out because it's on top and bottom, I don't have days anymore, now I have hours. Well, I'm getting closer to where I want to be. And multiply by another ratio. I know that 1 hour is the same thing as 60 minutes. So when I multiply my string of ones together, again, I have not changed the size, but I have changed the unit because hours now cancel out and I have minutes. So I'm one step away. I need one more ratio. and that is the fact that I know that 1 minute is the same as 60 seconds. So minutes now drop out because they're on top and bottom. And all of my units are now canceled off except for seconds. And that was my target unit. So because all I've done is multiply by 1 a bunch of times, it's still the same amount of time. But the difference is now instead of in years, it's in seconds. So I multiply 365 times 24 times 60 times 60. And whatever that product is, I'm going to divide by, it's 1 times 1 times 1 times 1, and that gives me the number of seconds. I'm not going to do the arithmetic, but if I did, I would know my answer is right because dimensional analysis guides me right to the correct answer. Let's look at another example. How far is a mile in inches? So again, we'll start out with our beginning point. What do we know? 1 mile. And then we know that we're going to multiply by 1 as many times as it takes to get our answer to have a unit of inches. That's our goal. So one thing that I could do is I could use the equivalency that we just looked at in a previous slide here, that 5,280 feet is 1 mile. Because these are the same length, I'm just multiplying by 1. So I have not changed my distance, but what I did do is I changed my unit to feet if I multiply these two quantities together. Let's keep going. I know that 1 foot is the same thing as 12 inches. So feet cancel. I've now changed my unit to inches, but because I multiplied by an equivalency, I have not changed the length. I've just changed the unit that I'm expressing it in. And I'm there. Inches is what I need. That's my target unit that I was shooting for. And I've now multiplied by 1 appropriately enough times to get there. So now the arithmetic is the only thing I have left to do, and that is to multiply 1 times 5,280 times 12, and then divide by 1, basically. Dimensional analysis is a place that you often have to think about significant figures because you're multiplying with measurements. But in these two cases here, 5,280 feet and 1 mile, and 12 inches is 1 foot, we don't have to think about significant figures. They're not part of our thought process because they're definitions, and so those are exact numbers. And that happens a lot when you're using dimensional analysis for something like just converting units. Prior to these days when we have many ways to convert, lots of apps and websites will convert for us from one unit to another. This was a really common use of dimensional analysis, was to convert from one unit system to another unit system. And it still works great, but there are now more efficient ways to do that if you happen to have your phone or a computer with you. But this is not the only good use of dimensional analysis. It's useful for lots of problems. Here's an example that we can solve with dimensional analysis. If the density of aluminum is 270 grams per cubic centimeter, what is the weight of 30 milliliters of aluminum? So we'll start this about the same way. We're going to start with a given quantity. In this case, it's 30 milliliters. That's the amount of aluminum. And we want to end up with a weight, which probably would be expressed in grams. So we're going to multiply by equivalencies until we get the unit that we want. Well, one fact I have that could be used as an equivalency is that 2.70 grams is the same as 1 cubic centimeter if you're talking about aluminum. But this is not cubic centimeters, it's milliliters. But there's another equivalency that we learned about earlier in the year that says that 1 cubic centimeter is the same thing as 1 milliliter. So that's an equivalency that allows me to change the unit because milliliters is going to cancel. When I multiply these two factors together, my volume is now expressed in cubic centimeters. Now I can use my density as an equivalency, as a factor in the dimensional analysis here. So I'm going to put 2.70 grams on the top because I want grams in my answer, and I'm going to put 1 cubic centimeter in the bottom because I want to cancel cubic centimeters off. Now, this compound unit, 2.70 grams per cubic centimeter, that implies that there are 3 significant figures down here too, if you're thinking about sig figs. So we'll have the same number of significant figures in the top and the bottom. Cubic centimeters now cancels. I planned it that way so that I will only have grams left, and that's my answer. So now the result is 30 times 1 times 2.7 divided by 1 times 1, and that will give me the number of grams. And I know I'm right because I multiplied by ratios that are the same as 1. Even though dimensional analysis is a super powerful tool that you can use in lots and lots of different situations, it's not universally applicable. Sometimes it doesn't work. There are 2 requirements that we need to think about before we use dimensional analysis. The first one is there a linear relationship between the 2 factors that are in your equivalency? So in other words, if you put the numerator and the denominator on 2 axes of a graph, would there be a straight line? If that's true, well, then you can probably use dimensional analysis. If it's not true, then you definitely cannot. So if you had some other kind of a relationship between the 2 quantities, like a parabola or a hyperbola, something like that, you would not be able to use the linear relationship. So you might be thinking, well, this is a hassle if I have to graph everything before I know if I can use it. But you don't actually have to, because you can just ask yourself a kind of a simple question. Does the relationship between these 2 quantities that I want to compare in this equivalency, does it change as one of them changes? Think about the examples that we used before. A mile and 5,280 feet. If it's 2 miles, well, it's just double 5,280 feet. The second mile isn't more feet than the first mile. So that's a pretty obvious one. Or density. Does the first cubic centimeter of aluminum weigh less than the second cubic centimeter that you add? No, it doesn't. Every cubic centimeter weighs the same. So the relationships are unchanging, and that's often the case. You can just ask yourself this simple question: does the relationship between these 2 quantities change? And if it doesn't, if that ratio is always going to be consistent, well, then you can use dimensional analysis. And the second restriction is that the line has to pass through the origin. So if you made a graph, first of all, it would have to be linear, but not only that, the relationship between these 2 would have to pass through 0, 0 on a graph where one of the variables in the equivalency would be on one axis and the other would be on the other axis. So that would work. But if you have a straight line relationship, even if it is linear, but it has a vertical intercept that isn't 0, then you can't use dimensional analysis. You're going to have to use some other kind of a technique. And again, you might be asking yourself, well, if I have to graph this to figure out if it passes through the origin, this is really not all that helpful. And again, there's a simpler question you can ask. You don't actually have to graph it. You can just ask, when one of these quantities is 0, is the other also 0? So thinking about 5,280 feet in a mile. If you have 0 miles, you also have 0 feet. So yeah, this relationship passes through the origin. Or density. If you have 2.70 grams of aluminum for every cubic centimeter, and you don't have any grams, you also don't have any cubic centimeters. So this simple question will allow you to decide if this requirement is also met. So there are many, many situations where dimensional analysis is appropriate. And it shows up in chemistry a lot, that you can use dimensional analysis to convert from one quantity to another quantity, because lots of our relationships fit these 2 requirements. They're linear, and when one is 0, the other one is also 0. And so we can apply dimensional analysis to solve all kinds of problems. And for me, it's a go-to technique when I'm not exactly sure how I'm going to get to the right answer.